Hello dear students, welcome you all. So students, today we are going to start solving the question paper of house examination which took place in the month of December 2024, right? So you can see here the question paper of statistical and thermal physics, right? This is the question paper of statistical and thermal physics, right? This question paper has three sections: section A, section B, and section C, right? Section A contains questions of very short answer type, whereas section B and section C contain big questions with the choice. In section B, you have to attempt any two questions, whereas in section C also you have to attempt any two question out of three. So this paper was of 30 marks and the time allowed was 2 hours, right? So now today we will start solving this question paper section wise. So today we will focus on section A, which is basically based on short answer type questions. 5 questions are there. You can see all these questions, right? So the first question was, what is probability and what is its range, right? So you know very well, I have told you in the class also what is probability. Probability is simply defined as the chance of occurrence of any event, right? You know, when you toss a coin, two possibilities are there. Either it is head or it's a tail. So if I want to find the probability of the occurrence of head, then I must have a number which can tell us that what is the chances in mathematical form, right? So mathematically, probability is defined as, it is defined as, you can see here, P is equal to small n upon capital N. Here small n, this small n, number of favorable outcomes, right, for that particular event for which we are finding the probability, whereas capital N, it is the total number of outcomes in that event. So if I took the case of this tossing a coin, then obviously capital N is equal to 2. Two possibilities are there: either it is head or it is tail. So two outcomes are possible. But if I am finding the probability of getting head, then N is 1. So it means this number will become, probability will become 1 by 2. Means there are 50% chances there to getting head. Same is the case in the case of tail. When you get the tail, again 1 by 2, and the probability will be 50% chances will be there, right? So I have also asked you that what is the range, right? What is the range? So I have told you in the class also that the range of probability is from 0 to 1, right? 0 means there is no chance of occurrence of that event, right? 0 means there is no chance of occurrence, clear? Whereas 1 means there are 100% chances that the event, that particular event will occur, right? So this is the range of the probability, 0 to 1. So this was the very simple question asked from the first chapter of your course, right? Now I'm coming to the second question. What is phase space? Give an example, right? So it is mentioned here. What is phase space? Give an example, right? So again, if I talk you about the phase space, first of all, we have to see actually what is phase space, right? So phase space basically means when we are dealing with the problems of statistical physics, right? And we are analyzing a system, right? Then in that case, we require both position as well as momentum, right? So this combination of position space and momentum space, this is called phase space, right? This is called phase space, right? I have told you that phase space is 6-dimensional because we require 3 dimensions for the position in normal cases, and three dimensions for the momentum. So this is about the phase space. Phase space is basically a combination of position space and momentum space that is required to describe any dynamic system completely. Clear? So this is the definition of phase space. I have also asked you that give an example. So I have gone through the your answer books. Nobody have given an example. So you have large number of examples there, and I have also discussed these examples in the class also. Uh, let's take the case of a simple pendulum. You can see here, this is the simple pendulum that is oscillating in this way. So this is the oscillations, right? So if I, draw the graph between the position and velocity, then this is the graph, right? You can see here, this is the graph. This is a phase space for this simple pendulum. Means this simple pendulum will exist in this region, right? This is the trajectory of the phase space. Clear? Its position as well as velocity will lies within this region. But if we have this type of pendulum, right, that is making a zigzag, right? This is a very stable pendulum that is oscillating freely without any disturbance. But this pendulum is undergoing disturbance. Then its uh, trajectory of phase space will become like this, right? It ultimately get stopped here, right? So this is the trajectory of the phase space, right? So you can give example in this way of a simple pendulum or a simple harmonic oscillator, or a large number of examples are there which you can quote for phase space, right? Now then I'm coming to the next question. It is C. What is the need of quantum statistics? Right. So again, why we need quantum statistics? I have told you that in statistical physics, you know, uh, the entire statistical physics can be classified into two categories, right? Classical statistics and quantum statistics. So what is the difference between these two, and why we require, the question was why we need quantum statistics, right? Classical statistics is used to deal with those particles which are identical as well as distinguishable. I have explained it thoroughly in the class that in classical world, even when the particles are identical, we can distinguish between them. But in quantum world, when we have two identical particles, for example, two electrons, then in that case, the normal, physics, the normal knowledge that we use in classical world, that is not applicable there. So, because in that case, the particles are identical as well as indistinguishable. So, to deal with these kind of particles, which are identical as well as indistinguishable, we need a new branch of statistics, that is quantum statistics. Also, there were large number of phenomena which could not be explained by this classical statistics. For example, the spectrum of black body radiation, right? This is the major problem which quantum statistics solved. We have derived, Planck's distribution law in that chapter in which we deal with Bose-Einstein statistics, right? So this was the answer of this very simple question, that why we need quantum statistics. We need quantum statistics to deal with quantum systems, because in quantum world, the particle are identical as well as indistinguishable. So the normal, classical statistics which deals with identical as well as distinguishable particles, that is not applicable here, because in quantum world, the identity and indistinguishability are linked with each other, right? This was the answer of this question. You can write it in 2 or 3 lines, right? Now I'm coming to the next question. D. Define Planck's constant and what are its units and dimensional formula, right? So again, I'm coming to this Planck's constant. You all have learned about the Planck's constant. We know according to Planck's law, E is equal to h nu, right? E is equal to h nu. E is equal to h nu, right? There was some problem with the pen. So E is equal to h mu, right? So this is Planck's formula. Here h, this h is Planck's constant, right? So if I write it in this way, h is equal to E upon nu, right? So Planck's constant is basically defined as a universal constant which gives the relation between energy and frequency associated with electromagnetic radiations. Because in case of electromagnetic radiations, photons, E directly proportional to nu frequency, right? So if we uh, go further, then E is equal to h nu. So this is Planck's constant h here. So I have also asked you what are its units, dimensions, and what is its value. So it is a constant, so its value is it is 6.62 into 10 raised to power minus 34 joule second, right? So this is the value of Planck's constant, right? And now here it is joule second units. I have also explained in the class that Planck's constant has the dimensions of angular momentum, right? So if you write down the dimension formula for this Planck's constant, then it will come out to be the dimension formula of angular momentum, right? It is you can drive it also from here. E is equal to uh, h is equal to E upon nu. So h is equal to E upon nu. So as far as energy is concerned, we know the dimension formula of energy is m L square T minus 2, right? Divided by what is the dimension formula for frequency? Per second. Per second means time inverse. So time inverse minus 1. So if you take that in the in nominator, you will get m L 2t minus 1. So this is the dimension formula for Planck's constant, and it is the dimension formula of angular momentum L. Clear? I have told you that Planck's constant has the dimension formula of angular momentum, right? That's why the spin of all the particles is expressed in terms of h cut. Clear? Because spin is linked with spin angular momentum. This is the reason why we express spin of elementary particles in terms of h cut, right? So this was the answer to this question. I'm coming to the next question. Last question. Define Fermi energy, right? Define Fermi energy. So I have told you what is Fermi energy in the class also. We have discussed it in detail. Now Fermi energy, it is defined, if we go to the definition, then Fermi energy is defined as the energy corresponding to that level above which all the energy levels are fully empty and below which all the energy levels are fully filled at 0 Kelvin of temperature. Clear? If we take the case of 0 Kelvin temperature, this is very important. 0 Kelvin temperature, then definitely have this. If these are the energy levels, right, first, second, third, so on, then there will be a particular level. Suppose if this is the level, uh, topmost field level at 0 Kelvin. This is the topmost field level at 0 Kelvin. Then all the levels below to this level are fully filled, whereas all the levels above to this level are fully empty at 0 Kelvin. So this level. This level is called Fermi level, and the energy corresponding to this level is called Fermi energy. So this was the simple answer to this question. That has been asked here. Define Fermi energy. The energy corresponding to the topmost field level at 0 Kelvin temperature is called Fermi energy. All the levels above this energy levels are fully empty, whereas all the energy levels below this level are fully filled. So, well, students, this was all about the section A. I have explained it thoroughly, how you have to answer all these questions, and these are very important questions which are also asked in the final examination also. So in the next lecture, we will come to the section B, right? We will discuss section B. So thank you very much.